In this video lecture, we're continuing with Chapter 18, and we're looking at sections 5 and 6. So in this section, we're introducing Gibbs free energy. And this slide is a derivation of an equation that we'll be using. So I'm just going to go over this derivation. Again, you won't be tested on it. It's just nice to see where equations come from when we can show you easily. So we talked about in the last lecture, delta S surroundings equals negative Q of the system over T. And from Chem 101, we learned that Q system equals delta H system. And we know from the previous slide as well, delta S universe plus delta S equals delta S system plus delta S surroundings. We substitute in negative delta H system over T. And now we're just going to do some algebra to rearrange. Multiply both sides by negative T. We end up with negative T delta S universe equals delta H system minus T delta S system. And rearranging this, now we can see we're going to define negative T delta S universe as the Gibbs free energy delta G. So this is a useful equation that we will be using a lot. Delta G naught equals delta H naught minus T delta S naught. And looking at the algebra of this equation, we can see when delta S universe is positive, and remember an increase in entropy, which is positive delta S, is favorable. Delta G is negative. Therefore, when delta G is negative, a process is spontaneous. So what we're going to see is negative delta G tells us the reaction is spontaneous. Always. As in Chem 101, we talk about exothermic reactions tend to be spontaneous, right? Exothermic negative. And we talk about in Chem 102, we have an increase in entropy that is favorable. So now what we're seeing is if I have a exothermic reaction with an increase in entropy, the reaction is going to be always spontaneous because delta G must be negative if we have a negative delta H term minus a positive delta S term. And the reason for that, remember that temperature is in Kelvin, which only has positive values. So another way of looking at this, if delta G is negative, we can say the forward reaction is spontaneous. So that would be in this direction. If delta G is 0, we're going to call that equilibrium. So equilibrium would be right at this lower point, and that would be when Q equals K and delta G is 0. If delta G is positive, the reaction is spontaneous in the reverse direction. So that's what we're looking at here, the spontaneous in the reverse direction. So a negative delta G, the forward reaction is spontaneous. A positive delta G, the reverse reaction is spontaneous. And this makes sense. So remember, if I have an equation, reactants go to products, if delta H, let's say, equals 5 kilojoules per mole, and let's say delta G is negative 10 kilojoules per mole. If I reverse the reaction, so now I'm looking at products going to reactants. Remember, if I reverse the reaction, delta H changes signs. That would be negative 5 kilojoules per mole. And the same is true with delta G. If I reverse the reaction, I change the sign. And this is true because they're thermodynamic state functions. So in this case, I have an endothermic reaction that happens to be spontaneous. If I reverse the reaction, it's now exothermic and non-spontaneous because positive delta G. We'll be looking at that a couple more times throughout this chapter. So let's look at this practice exercise 5. A particular reaction has a delta H of 24.6 kilojoules and delta S at 132 joules per Kelvin at 298 K. Calculate delta G and figure out, is the reaction spontaneous under these conditions? So a couple things to remember. Conversions we're going to need to use Remember, kilo stands for 1,000. So 1 kilojoule contains 1,000 joules. And the reason I'm going to need to convert that is because I see my delta S has units of joules per Kelvin and delta H has kilojoules, so they're going to need to cancel. Lastly, I want to get delta G naught, so for standard conditions, and I'm given delta H naught and delta S naught, so I know the equation that relates these is going to be the one that we just went over. Delta G naught equals delta H naught minus T delta S naught, where temperature must be in Kelvin, and that's what we have. So to use this, I know I need to convert either delta H and delta S both to joules or both to kilojoules. As you're going to see when you work through the homework, typically delta G is usually in units of kilojoules per mole. So I typically convert my delta S to kilojoules per Kelvin first. So I know if delta S equals 132 joules per Kelvin, I can say that 1 kilojoule contains 1,000 joules. So we're just dividing by 1,000. Easy to do in our head. And now I'm ready to solve the problem. So delta G naught equals delta H naught, which is 24.6 kilojoules, minus T, 298 Kelvin, times my delta S value of 0.132 kilojoules per Kelvin. And I can see that my Kelvin's going to cancel, and now I'm subtracting kilojoules from kilojoules, which is what we are required to do in terms of the algebra. The units have to be the same if you're subtracting. And when I put this into my calculator, make sure you plug this in, see what you get. I ended up with negative 14.7 kilojoules. And so delta G in kilojoules per mole or kilojoules, depending on the problem that you're asking. So those units make sense. And the negative delta G, remember, tells us that the reaction is spontaneous. So again, we're given delta H and delta S. We find delta G using our equation, delta G equals delta H minus T delta S. We confirmed our temperature was in Kelvin. We converted our units of entropy to kJ per Kelvin, and we end up with a delta G in units of kilojoules. On an exam, I would tell you I either want your answer in kilojoules or joules, so you would know which way to convert. For delta G, you are most likely to see a request and answer of kilojoules. Now we're going to look at standard free energy changes and another way to calculate them. So in this previous exercise, we looked at calculating delta G from delta H and delta S. And that's why we use this equation, because we're given delta H and delta S. What we're going to look in this next slide is what do you do if you're given delta G of formation of the products and the reactants. So we can use this equation. Delta G naught is the sum of the molar coefficients times the G of formation of the products minus sum of the molar coefficients times the delta G of reactants. And this is exactly what we did in the last lecture with entropy, and this is exactly what you did in Chem 101 with enthalpy. So we're going to review this one more time. And how would you know to use this equation versus the previous one? You'd be given your delta G values versus a delta H and a delta S value for a reaction. So here I can see I'm given my delta G values for different chemical formulas, and we're asked to calculate delta G for the combustion of methane. So it's important to remember, I would tell you what methane is, but you could also figure it out, because it's the one chemical formula you're not familiar with. Methane is indeed CH4, it's a gas. And combustion, that means I'm reacting something with oxygen. For reaction only, right? Combustion, it's going to convert all of the reactants to products until you run out of your limiting reactant. All of our carbon turns into carbon dioxide, and all of the hydrogen is converted to H2O vapor because it's at high temperature. Looking at that, no, we need to balance it. We've got 2 H's on the left. 4 H's on the left, I need 4 on the right. 1 carbon on both sides. I can see now I have 2 and 2 is 4. O is on the left, on the right, so I need 4 on the right. Now I can go ahead and look at my products minus reactants equation. So delta G naught for the reaction is going to be, again, products first. So I've got 1 mole of CO2 times the delta G naught value of CO2, which is negative 394.4, and the units are kJ per mole, plus 2 moles of H2O gas times negative 228.57 kJ per mole. And that is the math you need to do first, and then you're going to subtract 1 mole of CH4 gas times negative, can't forget that, negative 50.8 kJ per mole plus 2 moles of O2 gas times 0. So remember, on the calculator, you need to multiply and add before you subtract. So take a minute and put that into your calculator. Pause the video if you need to. And the value I got for delta G naught of the reaction is negative 800.7 kJ. And I know this is kilojoules because my moles cancel, right, as I multiply that with 0, so we would have a mole. So moles cancel, it's all in kilojoules. And again, why did I use my products minus reactants equation? Again, this equation that we went over before, because I was given delta G values for all of the reactants and products. So make sure you're comfortable using this equation because you will see it on our next exam. And over here, why did we use our delta G equals delta H minus T delta S equation? Because it was given delta H and a delta S, and asked to find a delta G. So it all depends about what you're given and what you're asked to find as to which equation to use. So let's go ahead and look at practice exercise 7. Consider the combustion of propane to form CO2 and H2O gas at 298 Kelvin, and you're given the chemical equation. Again, if I gave you the chemical formula of propane, you should be able to write this. Right? Combustion, you're reacting with oxygen gas. All of the carbon turns to CO2, hydrogen turns to H2O gas. And the question asks, would you expect delta G to be more negative or less negative than delta H naught? So this is a conceptual type question. So a couple things to think about. Combustion of propane. I know once I ignite the propane, the reaction happens. That tells me I know the reaction is spontaneous. So my delta G naught is going to be negative. The next thing I need to think about is delta H naught. So I know combustion is exothermic. I'm burning something, in this case propane, so my delta H naught is negative. Lastly, I can look at this reaction and determine the sign of my delta S naught. So looking at the chemical reaction, again, states of matter is the most important thing. We're all in the gaseous phase. So what I can look at, I can see I have 1 and 5. I have 6 moles of gas on the left, converting to 7 moles of gas on the right. So if I have an increase in my moles of gas, I know that delta S is going to be positive. So now I want to think about my equation that relates all of these. Delta G naught equals delta H naught minus T delta S naught. And we know that delta S is positive. We know that delta H is negative. So now we have to think algebraically what's going to happen to this sign of delta G. Will it become more negative or less negative than delta H? So if I have a negative delta H value minus a positive, that means my delta G must always be more negative. Than delta H naught. And we can think about that if we put in numbers, just make numbers up. So let's say delta H naught is -5 minus, let's say T delta S term, it's positive, so that's all that matters. Let's say it's positive 10. I know that when I put those together, my delta G is going to be -5 minus 10 is -15. So I can see that delta G is indeed more negative than the delta H. And plug in a variety of different numbers, and you're going to see as long as your delta H is negative and your delta S is positive, this is indeed true. In the next video lecture, we'll be looking at more of these relationships between the values or the signs of delta H and delta S and delta G. So make sure you work through this practice exercise before you start the next video lecture.